Hello my friends and welcome to the practical activities of part 3 on the A3C model. I'm super excited because now we're getting even closer to mimicking human intelligence because indeed we're adding to our AI a critic sense. In addition to, of course, first the brain that we were able to build in part 1 and then the eyes that we were able to build in part 2. And so indeed that's the human intelligence feature that we're adding into our AI for this part 3, which is a critic sense, which is brought, of course, by the critic agent in the A3C model. So you will see it will be super exciting to implement that. And so there we go. Let's not wait. Let's start right now. So remember in part 1, we built an AI and trained it to land on the moon. In part 2, we built an AI and trained it to play a game. And now in part 3, we're going to build an AI and train it to fight Kung Fu. Alright, so let's do this. We're going to go now into the environments. We're going to go into Atari, of course. And then we're going to scroll down. We're going to click here, see more environments. And we're going to scroll down to K to find Kung Fu Master. Here we go a bit more. And here it is, Kung Fu Master. So let's have a look at the environment. That's always the first thing we should do when we build an AI, to understand the environment, to understand what is the action space, what is the observation space, and how the reward system works. So there we go. The action space is composed of 14 discrete actions. So let's have a look at them. We can find them in more details below. Actions, there you go. So these are all the actions. So the action of index 0 will be do nothing. Then action of index 1, up, which means probably jump. Action of index 2, go to the right, then go to the left, then down, meaning probably kneel down, then down right, down left. Okay, so these are all the fight moves. You see right fire, left fire, down fire, up right fire, up left fire, down right fire, and down left fire. Okay, so we have all these actions. However, these are the actions of the Kung Fu Master V5 environment. And again, you know, in order to not have a too long training that requires too much compute resource and memory, well, we're going to take a simpler environment than this one, and it's going to be, once again, one with a small part of deterministic action. So we're going to go for the Kung Fu Master Deterministic V0. Indeed, it is simpler because a small part of the actions of the other agents, meaning the monsters, you know, the enemies which we have to fight, or I mean which our AI has to fight, will be deterministic, but that's only a small part of them, just in order to decrease the complexity of the environment and therefore offer us a faster and easier training, which is good, you know, for educational purposes, because I really want every one of you to be able to train your AI and enjoy the results at the end. So we're going to go for this one, Kung Fu Master Deterministic V0, and anyway, we will have a look at the actions again in the implementation, so we will know exactly what the action space is. And for the observations, well, of course, there are going to still be images, right? Each time we are progressing closer to mimicking human intelligence. So in the last part, our progress was to add some eyes to our AI. So of course, now we're going to keep those eyes and we're going to add a critic sense. But therefore, since we're keeping those eyes, well, the input states will still be images of these dimensions, which we will resize, of course. Okay, so we have it here. These are the dimensions of the images, 210 by 160 by 3, the 3 RGB channels. But of course, we're going to resize that again in order to decrease the complexity for the training. All right, so I think we're good here. And what about the reward? Well, the reward, just like last time with Pac-Man, the reward is going to be the score. That score that we see here, you know, it starts at 0. And well, if we kill some, well, I mean, if our agent, our AI kills some enemies and, you know, avoid some bullets and progresses in the game, well, the score will increase. Right now, we don't see it increasing because apparently the AI is doing nonsense actions. But there you go. You will see at the end, we will get some nice results with that score increasing over an episode. And hopefully, we will reach a good score. If our AI already reaches 500, well, we'll see it already able to fight quite well. Maybe not like Neo in the Matrix, but still definitely better than me. Okay, so let's do this. Let's go into our implementation. So I copied before the link that was provided to you just before this tutorial, the link, of course, of the Google Drive folder containing all the codes of this course. And so there we go. Now we're going to go into part 3 A3C. And again, you will find 2 implementations, 2 notebooks, the complete code 1 containing the whole code and all the results and everything. But I recommend not looking at it right now so that we can practice and code everything together first. And speaking of which, well, that's what this partial code notebook gives us. Indeed, this code only contains the code cells that are not related to building an AI, and inversely, all the cells related to building an AI were removed so that we can recode them together as we should. We should practice the maximum and really know and understand how to build an AI on a practical level. So let's do this. Let's open this notebook, A3C partial code, and here it is. But remember, this notebook is in read-only mode, and therefore no one can do any modification on it, code on it. Therefore, we're going to go to File here and then click Save a Copy in Drive. And this will create a copy in your drive, which you will find in your Colab Notebooks folder. Here it is, copy of A3C Kung Fu partial code, and now you are the owner of it. Therefore, you can modify it and code on it. So, perfect, we can now start. But first, let's rename that to A3C for Kung Fu partial code. I'm just going to remove the copy of here. And there we go, now it's better. So now you have all the 3 codes, of parts 1, 2, and 3, and of course excluding the LLM code for generative AI. So again, congratulations for having reached this far in the course. So there we go. Let's open this new notebook, which now belongs to us. We are the owner of this notebook, and therefore we can code on it and implement our new, even more powerful and even closer to human intelligence model, the A3C model for Kung Fu. So let's start the implementation in the next tutorial, and until then, enjoy AI. Hello my friends, and welcome back to this implementation of A3C for Kung Fu. So before we start, I just want to show you the structure of our implementation, because it's good to have a bird's eye view of what we're about to implement before we do the implementation. So as usual, we start with the part 0, where we will be installing the required packages and importing the library. So it's always the same thing. We just need to install Gymnasium thanks to Google Colab, where indeed most of the libraries and packages are already pre-installed. So we will just install Gymnasium. Well, actually, let's run the cell right now, because it takes a little time to install indeed Gymnasium and the environment. Alright, so here we go. It is now downloading Gymnasium. It's downloading the dependencies like format notifications, etc. Just like before, right? It's exactly the same. It's the exact same code cell, and we will have the same dependencies being installed, auto roam, and etc. So the cell will be running now. The dependencies will be installing. Successfully built auto roam, successfully installed auto roam, reading package list done. Everything looks good, just like before. Processing triggers, downloading Box2D, building wheels for collected packages Box2D for Python, and in a few seconds we'll have our Gymnasium. So that's perfect, that's exactly like before. Then the next step will be to import the libraries, and so here, well, same as before, but this time in the import I included the Gymnasium libraries and modules or classes that we will use from Gymnasium. So there we go, it's included here. And so once this cell is done, meaning once Gymnasium is installed, well, we will be running the cell to import the libraries that we will need in this implementation. Of course, we'll have a few more libraries to import later on, but I try to include the maximum of them. Successfully built Box2D-py, perfect installing collected packages, Swig, Box2D-py, and there we go, successfully installed Box2D Python. You might have a different version when you take this course, but that's fine. We will always keep the code up to date whenever something is out of date, okay? And I might even re-record some tutorials if some codes or module expire. Alright, so great, so now we have Gymnasium, so we're gonna import the libraries, okay? So same, we import NumPy to work with NumPy arrays, we import the random library to generate some random variable, we also import, of course, all the Torch, library and modules, such as the NN neural network module to build our neural network, but also the Optim module to build our optimizer and use it to update the model's parameters, meaning the weights. We also import the functional module to, not only use the activation function, but also to use the loss function, when we backpropagate that loss between the target values and expected values. And then we import some other modules, such as distributions by the Torch library. And there we go, Gymnasium, observation wrapper, and box for the environment. So with this, we'll almost have everything we need. We'll have a few more imports later on, but that's okay. Let's start with this. Let's import the libraries. Alright, so it's importing the libraries now, and in a second we will have all the libraries imported. And once again, we didn't have to install any of those modules and packages because it is already pre-installed in Google Colab. That's the beauty of Google Colab, and that's exactly why I wanted us to work on Google Colab. This makes our life much more easy. Alright, so now let's have a look at the structure of the implementation. Just like before, we're going to start with part 1, building the AI, where of course we're going to create the architecture of the neural network. So once again, the neural network of our A3C agent, our new AI, will have fully connected layers representing the artificial brain just like before, but also convolutional layers which represent the eyes. So we will include all that, of course, and besides we'll make that forward function to forward propagate the signal from the input images up to the final output layer, passing through the convolutional layers first and then the fully connected layers. Alright, so we'll do all this, and that critic sense that we're adding to our AI, that extra feature which will make our AI closer to human intelligence, well, won't be implemented in this architecture. It will be implemented in the A3C algorithm, okay, which we will do later on in part 2. And well, speaking of part 2, well, that's of course about training the AI, because of course once we have our brain here and our eyes, well, it will be time for us to train it to fight Kung Fu, okay? So how will we do that? Just like before, we will start by setting up the environment, right? Same first step of part 2, although this time we have to use this much more advanced pre-processed Atari class, which will make our environment fully ready for our AI to be trained and fight Kung Fu. Okay, so no need to implement that at all. It's not really related to building an AI. So let's just save us some energy here to focus on the real deal, which is of course all the cells that come after, meaning initializing the hyperparameters of our AI, the A3C agent, then implementing the A3C class, then initializing the A3C agent, then evaluating our A3C agent on a single episode. We will need that in order to measure the performance of our A3C agent during the training. Then of course we'll test multiple agents on multiple environments at the same time in a function so that we can indeed implement the A3C algorithm. And finally, once we have all that, we will train our A3C agent in a nice loop. And once done, we'll get some good training results, hopefully, and we'll move on to part 3 to visualize the results. And here, that's the exact same code as before, with the show video of model function first and then show video, and then we'll get the video at the end of our AI fighting Kung Fu. Alright, so I hope you're excited. I'm super excited to start this implementation because indeed this is the most powerful model of this course. Indeed, with that critic sense added, it will really make our AI more artificially intelligent. So there you go. I can't wait to start the part 1 of this implementation, building the AI. So take a good break. Again, we'll have a big architecture of our AI's neural network to implement. So once you're ready, join me in the next tutorial and let's smash this. Hello my friends, and welcome to part 1 of this implementation, building the AI. I'm super excited to create the architecture of our neural network. We will, just like before, implement a network class which will include the whole architecture of our A3C model, which will contain of course the convolutional layers to build eyes, the fully connected layers to build neurons, and the forward method to forward propagate the signal from the input images up to the final output layer. Alright, so that's all we'll do in this new code cell, creating the architecture of the neural network, and indeed the rest of the A3C algorithm will be implemented later on in the agent class. Alright, so let's do this, let's create a new code cell and let's start the implementation. Great, so as usual we're going to start with class because we're going to define once again a network class just like before, which will inherit from the nn.module, meaning the module class from the nn neural network module by PyTorch. There we go. Then let's add some colon, and here we go, defining the constructor method init method. Alright, so let's do this. Let's start with def to define it, then double underscore init, double underscore again, and it will take, just like our deep convolutional Curie model, first self for the object and then the action size. Remember, the network class of the deep Curie model took as input here the state size and the action size. Then the deep convolutional Curie model took only the action size because for images the state size didn't make much sense. And now, well, since we're doing the same, since we still have input images and also eyes in our AI, well, we're only taking the action size. So far, exactly like the deep convolutional Curie model. Alright, so let's add some colon, and then remember, we're going to activate the inheritance with the super function, which takes as input our network class, the class that will inherit from the nn module, and then comma, and then self for the object. Alright, great, then we add here a dot, and then another double underscore init, double underscore, and parenthesis, inside which we don't input anything. Super, inheritance activated. Alright, so now let's define the convolutional layers, or more specifically the convolution operation. So we're going to start with the first one, self.conv1, just like before, which will be created as, of course, an instance of the conv2d class which we import from the nn module from the torch library. So that's why I'm starting with torch here, and then nn, calling the nn module, and then from which we call this conv2d class. There we go. Let's add some parentheses. And inside, well, remember, we have to input the number of input channels, the number of output channels, the kernel size, and the stride. So here we go. Let's start with the number of input channels. And so now remember, in the deep convolutional Q-learning model, we had 3 input channels here in the first convolution. But actually now we're going to have, guess how many? We're going to have 4. And what does this time 4 correspond to? Well, be careful, it doesn't correspond anymore to the 3 RGB channels for colored images, because here actually for our A3C model, we're going to have a stack of 4 grayscale frames from our Kung Fu environment. Alright, so that's why we have 4 here. And then, however, for the number of output channels, there it is, well, we're going to have, just like before, I think we had 32, right, in the deep convolutional Q-learning model. Let's check again. Or maybe 64, I don't remember exactly. Yeah, 32. See, we started at 32, then we increased to 64, 128, and you'll see how we will do now with our A3C class. Okay, so 32 output channels still here, and then we're gonna have a kernel size of 3 by 3, and finally a stride of 2. So once again, there's no rule of thumbs for choosing the optimal numbers here. We just have to do a lot of hyperparameter tuning, a lot of trial and error, and a lot of experimentation to end up with hyperparameter values that lead to a great score. And of course, a lot of experimentation was done on this A3C model for Kung Fu, and these hyperparameter values turn out to be quite good. Maybe not optimal, maybe you'll find better ones. If you do, please share in the comments, but these are quite good already indeed. Okay, so that's it for our first convolution, self-conv1. So now I'm going to copy it, of course. I'm going to paste it right below, and I'm going to replace self-conv1 by self-conv2. All right, self-conv2, here it is. So now what is going to be the number of input channels in the second, therefore, convolution? Well, that's, of course, the number of output channels in the previous convolution, meaning 32. And now, regarding the number of output channels in the second convolution, well, it's not going to be exactly like our deep convolutional Q-learning model where we increased the number of channels. However, feel absolutely free to try that. But in fact, we're going to stay at 32 filters. And again, that's because it leads to pretty good results at the end. So 32 output channels, and then the same kernel size of 3 by 3 and the same stride of 2. So actually, we're all good with our second convolution. So I'm going to copy it again, and just below I'm going to paste it, and I'm going to replace self-conv2 by self-conv3. Because indeed we're having another convolution with a third convolutional layers. And well, the good news now is that we don't have to change anything in this line of code, because actually, for our third convolutional layer, we still want 32 input channels and 32 output channels. So you see, it's not increasing this time. It doesn't have to increase all the time. For deep convolutional Q-learning, increasing the number of filters over the convolutions actually was better and led to a better score in the end. But here, we're having great results, but once again, maybe not the best ones with this architecture. But again, feel free to try some other architectures, and if you get a much better result at the end, well, please share that in the comments. I'm super curious to see your better architecture than in this tutorial. Okay, so that's gonna be it for our convolutions. Now we're gonna do something that we haven't done before in the deep convolutional Q-learning model, which is to create directly the flattening layer. Remember, in the deep convolutional Q-learning model, well, first we had the batch normalization layers, which we don't have anymore in our A3C model, simply because they don't really improve the results, but mostly, as you can see here, we didn't create the flattening layer. We directly moved on to the fully connected layers here. But here we're going to do something different. We're going to create that flattening layer within an object, which we're going to call self.flatten. And it's good that you know this also. You can create a flattening layer thanks to a torch class, which is actually the torch dot, of course, and n again, because this class belongs to the nn module. So torch.nn dot, and as you might guess, of course, well, flatten. The flatten class, which indeed allows us to create a flattening layer after the convolutions. And you will see, thanks to the forward function, how we forward propagate the signal from the convolutional layers to that flattening layer. Alright, and actually we don't have to input anything here because the transition will happen thanks to the forward method. And so we can directly move on to our fully connected layers. Okay, so well, let's do this. The next operation that comes after the flattening is, of course, the first full connection, and which we're going to call, of course, self.fc1, right? Just like before. And remember, we create that as an instance of the linear class by the NN module from the torch library. Therefore, we call first the torch library, from which we call the NN module, from which we call the linear class. There it is, and then we add some parentheses, and inside the parentheses, remember, we have to input first the number of input features, which is actually the number of outputs in our flattening layer. And for this, well, remember that we have this very complex formula that requires to be applied in the different operations and layers we had before. So we're not going to go into the details of that. I'll just tell you that number, which is 512. Okay? If you're really interested in knowing how we get to this number, well, feel free to ask ChatGPT. You just provide this architecture to ChatGPT. You ask ChatGPT to help you decompose that whole formula through the different operations and layers, and you will get to that 512 number at the end. Okay? But let's not spend too much time on this and move on with our following full connections and fully connected layers. So 512 for the number of input features, and now for the number of output features. Again, no rule of thumb, but a good number is 128. Okay? 128. Perfect. And now something very interesting is going to happen, and that is proper to the A3C model, therefore we haven't done before. What we're going to do now is actually directly move on to the final output layer, or should I say final output layers, because indeed, first, we're not going to have any second intermediary fully connected layer. We're directly going to move on to the final output layer, but mostly we're going to have two final output layers, right? Do you guess what they will correspond to? Well, the first one will correspond to the action values, which are of course going to be the Q values for each action, which is the expected return, meaning the sum of rewards starting from the current state. So that's exactly what we had in our previous models, right? The deep Q-learning and deep convolutional Q-learning model. So we're still going to have that here, but also we're going to have the state value, right? Which will be a single output of the network that will provide an estimate of the value of the current state. And that value is actually a prediction of the expected return from the current state if the agent follows the current policy. Okay, so we need both of these for the A3C model, and therefore we're going to create a second full connection, which we're going to call FC2A for the action values. And therefore, to create that, we're going to call first the torch library, from which we're going to call the NN module, from which we're going to call the linear class, which will take as input first the number of input features, which will be, of course, the number of output features we have in the previous fully connected layer. Therefore, I'm going to enter 128 here, and then, since this second full connection will return the final output layer corresponding to the action values, well, here we have to input, of course, the action size, okay, containing the number of possible actions. And therefore, the output of this second full connection FC2A will be the action values, meaning the Q values for each of the actions representing this expected return if we play that action from the current state. Okay, so that we know, but now what we also need to create is that second full connection leading to the final output layer containing the state value, and this one I'm going to call it FC2S, okay, for the state value, okay? And so for this one, what will be the number of input features here? Well, of course, that's going to be the number of output features here in the previous fully connected layer, therefore 128. This we don't change. However, what is going to be the final number of output feature here in the second full connection FC2S? Well, since we're expecting only one state value, of course, this final number is going to be 1. Okay? And that's it. That's it for the architecture of the network class for our A3C model. Now I guess it's time to take a good break. We did some good new work here to build this A3C model. So let's get some great energy, and as soon as you're ready, we'll implement together that forward method, which will forward propagate the signal from the input images up to the final two output layers. And until then, enjoy AI!